I had no sooner finished the previous video when it occurred to me that there was actually another equation I needed to point out in an application of something I'd shown that I really need to talk about just a little bit more. Here, let me just kind of add this little bit on to the last video about voltage. So last time we got together, on the video we talked about electric potential, this V guy, and potential difference, the delta V between two locations. And in particular, we talked about the fact that what potential is, we want to be able to assign a value to a location in space and say, hey, for every little bit of charge I put there, I would have this much energy stored up in that system. And so what we talk about is the potential energy per Coulomb that we would put at that location, right? And so when we did that, we said, okay, V is my UE per Q, right? Potential energy per charge. And it's going to be in units of joules per Coulomb, which we give a special name of a volt. So electric potential is in volts. If I talk about two different locations, we said we could talk about the delta V from here to here, the change in potential, the change in electric potential. And we say, well, that would just be the change in potential energy per Coulomb of charge that we move from there to there. How much our potential energy in our system would change for every Coulomb that we shift over. So what I neglected to point out, I didn't really focus on too much, was two things I can do with this. One, coming back to this, we used our potential energy equation, KQQ over R, and we divided out by the Q. It gave us this. And I did mention and say, hey, look, this is a way of finding my potential here this far away from this charge Q, right? But I should have emphasized probably that is another formula you can use. The potential from a point charge when I'm this far away from that point charge, right? Well, what I could mention is, well, what would happen if I had multiple point charges? Well, then I would just add up all the KQ over Rs. Makes sense? I take the potential from this charge. So if I had some sort of an arrangement, like, look, I've got Q1 here. Oops, that's the wrong color. See, I've got a charge here. Look, here's a Q1, and here's another Q1. Q2, and maybe another charge here, and some arrangement, right? Look, here's Q3, and I want to find, hey, right here at this location, right there, what would the potential be? Well, I would just add up my potentials from all these guys. You say, oh man, this is going to be like we found E field, and we add up all the KQ over R squareds, right? Easier. With E field, big E is a vector. It's got a direction to it. And so I had to break into components. But this is just energy per charge, not force per charge. It's not something that's a vector. V is not a vector. And so what that means is I just have to define the V there. My V, I'm just going to add up all the KQ over Rs, but it's just simple addition. I'm not having to worry about components or anything because these aren't arrows that I'm adding. And so that's like so much nicer. Potential calculations are easier than field calculations because of this. It's a big difference. The other thing I want to point out is, oftentimes we'll talk about this, and like the next thing that we talk about is equipotential maps, equipotential diagrams, a way of visually representing this V level. And I don't want to dive into that, but just point out the idea that the more positive charges I have around, the more that total will get bigger and bigger, and my V value goes up and up. But if I start putting negative charges down, each one is negative, and we do include the sign of the Q, so the V level will go down and get reduced for every negative charge up in that area. Yep. Okay, so I just want to emphasize that this is a thing. That is a formula, and that we can do it with multiple charges, not just from one point charge. We can just add up all the KQ over Rs. And I know you know where we're going next with that. What if I don't have point charges? What if I had, a region in space with charge spread throughout it? Could I find my V value at different locations, outside the sphere, inside the sphere? You say, how would you do that? Well, of course, I would just take all this and I'd split it up into an infinite number of infinitesimally small charges. Each little charge would make a little dV made by each little dQ, And yes, that's what we would do. We would say that my total V would just be add up all the K dq over R's. And yes, we will do those calculations, okay, very soon. Okay, we will do that. Okay, there was another thing I need to mention, okay, I need to bring up and discuss with you. And that actually, remember that over here when I talked about electric field strength, we said, oh, the unit it's in, it's going to be newtons per coulomb, and I said, oh, there's another unit? Okay, that was alluding to this other thing I need to talk about. So I'm going to come over here. First, we talked about how V is my UE per Q. So delta V would be the change in energy per charge to go between those two locations. But you know what we could do with this delta UE per Q, right? I already have an equation for delta UE. So if I come over here, delta UE is this. So what I can do, I can say delta V is my delta UE per Q. So it'll be negative Q integral E dot dr. And divide out by that Q, bang, bang, and I get this formula. Delta V is negative integral E dot dr. This is a hugely important formula. It's like, to my mind, like, for the calculations we're going to be doing, it's like the most important. You know how force is important? Of course, force is important. Most important concept in physics. But when we talk about electrical stuff, we usually talk about the force per charge, E field. This is the most basic equation linking E field strength with voltage. Okay? And remember, voltage is special because we can directly measure it with a voltmeter. Bing, bing. And that's how we'll get an E field strength. Let's look at this in a little bit simpler case. My delta V is negative integral E dot dr, right? Now, let's say, special case, that you see that dot, there's an angle between the E field and the path going from A to B, right? Say I've got two spots here, position A, position B, and I'm trying to find my delta V from here to here, right? So I'm like putting up my voltmeter and measuring that delta V. If there's a difference in potential, right, there has to be an E field there, right? And if I'm going up, and say, think about it, if I go, let's just say there's an E field going to the right. If I was going, okay, so say we're going from here to here. Imagine, if you would, that I was moving a positive charge to the right. It's going with the field line. It's going with the electric force. Would it be gaining or losing potential energy, this field and charge system? If the charge is moving with the field line, right, if we're going this way, we'd be going with a positive charge would go with the force, it would lose potential energy, right? And so I would have my delta V would be negative. I have a loss of potential energy for that positive charge. It'd be negative over a positive, I would get a negative answer out, right? My delta V is negative E dot dr, that's cosine 0, which is 1. It works out right, okay? If I go with the E field, I go down potential. This is something important to know. We will talk much more about this when we start talking about E potential maps. But if I go with the E field lines always point to lower potential. And so, and I hope that makes sense. Like, I hope that makes sense. We could do another what if you want. What if I had a negative charge going from A to B? Well, if I had a negative charge, the E field would actually be pointing against me. The force of the E field would be going against the motion if I tried to move it negative from A to B. So I'd be pushing against the electric force to go there. The delta U, I'd be gaining potentially. Delta U would be positive, the charge would be negative, positive or negative. I still get a negative, my V level still goes down going that way. Because again, V is a property of the location. It doesn't matter what charge you push around. Going with the field lines, you're going to lower potential, to positions with lower V value. Okay, so it's kind of cool that it works that way for any charge. So the Q doesn't need to even be in the equation. Okay, the charge you're pushing around. find the delta V. But this brings me to that last point. I'm gonna tinker with this a little bit. So first of all, what if I had a uniform E field, kind of like I drew here? Then E would be a constant, and I could factor it out. And if that angle between the path and the field, right, is the same angle all the way through, which it is here in this case, then that cosine theta would be a constant, that dot could come. So what I'd get then is E would come out of the integral, the cosine theta would come out of the integral, just be the integral of dr, which is just to add up all the little drs. That would just be the distance I want, right? So what would happen to this equation then? If I did that, you say, for constant E and constant cosine theta, right? Right, constant angle between the path, the motion, and the field. Then what would happen? I would get delta V is negative E dot delta R. That's what we're turning to. I'm going to do one last little change here. I could rearrange this then. Let's move the negative sign over here and let's divide out by the dr. I would get that E is negative delta V over delta R. All right? Now what this is saying is, look, how strong is my field? That has to do with my change in potential per change in position. So it's like how much my V level goes down for every meter I go over. That tells me how strong the field is. And you say, well, wait, the V, that's how much potential energy I have stored up? The stronger the E field that I'd be pushing with or against, the bigger the potential energy change I would have for each charge per meter I go. For every meter I go along, if it's a stronger field I'm pushing against, it's going to be a bigger energy change. And so a bigger delta V. Isn't that kind of cool? So you can measure E field strength. You can't directly measure it, but you can directly measure delta V. And so you say, oh, my delta V per distance, that tells me how strong the field is. Cool, huh? So that's how we can actually measure a field. Now, there is a little sleight of hand here in this derivation I did. The sleight of hand is with this dot product. Remember that dot means there's a cosine theta there, and it mysteriously disappeared when I went from here to here. What does this mean? When I take a dot product, I'm really just taking the part of E that's parallel to the delta R, right? So what this is, what that means is, this is just the part of E that's parallel to R. It's like the E in the R direction. So if I made this, say, delta X, this would be the E in the X axis, the E component of E in the X. If I looked at the motion as I move along the Y axis, this is me the component of E in the Y axis, and so on. All right, just give me the part of the E field that's parallel. I'm getting ahead of myself, but the point is that if I do this then, say I have an E field, we'll go crazy here, in 3 dimensions, right? Going at some weird angle in space. It's got an X component, a Y component, and a Z component. I could just take this delta V, take measurements as I move in the X direction, in the Y direction, in the Z direction, and see how quickly my V is changing. And now tell me my E components in X, Y, and Z, and then I can use Pythagorean theorem in 3 dimensions to find the total E field vector. Okay, all right, I know that was probably a little bit further than I really wanted to go. But I will do this, last thing. All right, you say, this was for a special case, right? If I had a constant E and constant theta. Okay, what do we do when it's not constant? We're gonna leave it as the integral form now. What am I gonna do? I'm gonna, what this is saying is to look as I go along this path and split it up into a bunch of little, each little bit is a little dr, through little distance, little differential bit of distance, okay, dr. Going along, right? Well, what I'm gonna do is I'm just gonna look at one of those little motions, my E field strength times the little motion. If I did that, just one of these little pushes, not add them all up yet, that would be a little differential change in V. My E field divided with a little change in position, right? Now I'll move the negative sign over and divide out by the dr, and I'm getting that E is negative dVdr. Okay, and that is a formula for sure, right? Again, if I had a constant E field and a constant delta theta, I could just make this delta V over delta R, right? Or that'd be like an average value. Yeah, pretend it's something. An average value is like the one value you get the same result if it was a constant, one constant value that gives you the same result. So yeah, so if I had deltas, that would give me an average. But anyway, the point is, average E field, that's important for later. But the point is, remember, because of that dot, this is really just like, this would tell me if I look at my change in V as I go in the X direction, right? That would be my X component of E field. If I look at it as I move in the X direction, it's my X component. Or if I look at my delta dV dy, that gives me the E and the Y, and so on. Okay, there's a bit of math I could talk about here, but I think I'm going to save it for another day in class. But my point here that I want to get at is, okay, we just, in this video, what did I talk about? I talked about this, the idea that I can add up all the KQ over Rs to find the total potential from a system of particles. And if I a charge spread out in a volume or in some shape, then I could add up all the K dQ over Rs, integrate, right? Okay, the other thing I pointed out is that we have this formula for relating delta V and E field strength, right? That my delta V is negative integral E dot dr, and I indicated to you that this is going to be super important, okay, for what we're doing in this unit. Like, this is maybe the most important formula. We're going to use this for finding delta V's. If I have a function for E field strength, which this is what we did last unit, I'll stick that function in there and I give my delta V's. Okay, that's what we'll be doing a ton of. Okay, if I rearrange this and take the differential version of this, then you say, hey, what am I going to get? I'm going to find my component of E in this axis by doing negative dV dx. Okay, so if I had some function for V, I could take the derivative with respect to a variable to find the E field in that variable, in that axis, in that dimension. Okay, so that's it. Last little thing. Hey, what are the units here for E then, for my field strength? I'm going to take a potential difference measured in volts and divided by a change in position, right, measured in meters. So that means if I'm looking at my E in the generic R direction, maybe DDR, my units are going to be volts per meter. A volt per meter, then, is another unit for electric field strength. And hopefully that kind of makes sense to you. The stronger the field, the bigger the change in energy per charge I would have per meter of distance I go against that field. You know what I mean? The bigger energy change than move along the field line. So yeah. The stronger the field, the bigger the energy change for every meter that I go along it. That's all right. So that's stuff I wanted to introduce. Like I said, very soon we'll be talking about electric potential, doing these maps called equipotential diagrams, equipotential maps with equipotential lines. We'll talk about doing those and about how to interpret those diagrams. And they're cool. And then we'll move on to doing this stuff, finding my potential for different systems with charge spread out in different shapes and stuff, right? And then that'll be the potential stuff. And then we can move on and talk about capacitors, and that's the last part of the unit. So that's the plan. All right, just a few other little things to mention.